Hello, welcome to another lecture. This time, we're going to do a little introduction to probability. So we'll kind of lay the foundation for some tougher probability questions here. And let's go ahead and just get right into it. So we'll start off with some terms, with some definitions. And there's a lot right here on this slide, but they kind of every term here just kind of builds on the last one. So let's build these up and talk about them. So let's first start off with an experiment. So if I'm running any sort of experiment here, that's like saying I'm doing something like flipping a coin, or maybe I've got a stopwatch and I'm measuring a reaction time from someone, or just really anything that you could test, anything that you could do to sort of see what the outcomes might be. That's what an experiment is. And so maybe what we're doing is we're pinching someone and we're seeing how fast it takes them to flinch, and we have a stopwatch and we're timing them, or something like that. So that might be our experiment, and an outcome of that experiment is just the result of what happens when you do it once. So maybe you pinch someone and then it takes them a tenth of a second to sort of flinch and respond to that, and you measure that on the stopwatch. Well, that outcome is just that single result. And obviously, if we do it over and over, we'll have multiple outcomes. So as we keep doing this experiment over and over, we have multiple outcomes. And what we say is that when we have all those outcomes, there's going to be a lot of different possible things that can happen. And maybe we even change our scenario to like rolling a die, right? A six-sided die. And all the possible outcomes, you could get one, you could roll a two, you could roll a three, a four, a five, or a six. And all of those put together, that's what we're going to call our sample space. So if I was rolling a six-sided die, I might say, hey, the sample space is just that I can roll a one, two, three, four, five, or six. And there we go. What we'd say is that after that, so we have our sample space, which sort of lists everything that's possible. An event is just some subset of that sample space. So what I might say is, okay, I've got a six-sided die. Consider the event that I roll an even number. And so that right there would be saying, hey, I have a six-sided die. Well, the event of rolling an even number, that's me rolling a two, four, or a six. And so with this term event, we would say, it's something like, hey, what if I roll an even number? What if I roll an odd number? What if I roll a number less than five? Things like that. And those are all events. And then what we do is when we talk about an event, let's use this example of rolling an even number. We might ask, what's the probability of that event happening? What's the probability? What's the chance that I roll an even number? And that's just how likely it is to occur. So with a six-sided die, you could realize that there's six choices, one, two, three, four, five, and six. And if I'm talking about the probability of rolling an even number, that'd be 50% because I can roll a two, a four, or a six. So there's some terms right there. Most of the time, we'll just be talking about event and probability of an event, but it's good to know that an outcome is just the result of one trial, and the sample space is the set of all possible outcomes. So there we go. Let's talk about some rules of probability. So probability, which I'm going to denote by P, that it satisfies some rules here. And the first and foremost is that probability is always between 0 and 1. So it's going to be some sort of decimal, like 0.5 or 0.46 or something like that. And it's never lower than 0, so it's never negative, and it's never bigger than 1, so it's never larger than that. And that just tells us it's kind of like a percentage, right? If maybe I had a decimal, something like P equals 0.63. Well, I could convert that into a percentage and that's fine, but written as a number, it'll never be outside of this 0 to 1 range. If the probability of an event is equal to 0, that means that the event never occurs. And then likewise, if the probability is equal to 1, that means the event always occurs. And I want to be very clear on these two definitions here. In sort of real life, people will say, hey, what are the chances of this happening? And people go, oh, 100%, because they're like almost certain that it's going to happen. But in math, when we use these words never and always, we mean exactly that. There's no sort of ifs or ands or buts or anything like that. If we say p is 0, that means that there is no chance that it could happen. For example, I might say, what's the probability that I roll a 7 on a six-sided die? Well, the probability of that would be 0 because there is no 7 there. And then likewise, what's the probability that I roll something less than a 7 on a six-sided die? Well, that probability would be 1 because every number on a die is less than 7. And so be careful about these words never and always. That they really do mean never, never, ever, and always and every single time, no matter what. So don't use p equals 0 and p equals 1 colloquially. Use them mathematically. The last sort of rule that I'll mention is that if you look at all of the possible events that can happen and you add them up, that's going to give you 1. So looking at a die that I might be rolling, we could say that all of the possible events are that I roll a 1, I roll a 2, I roll a 3, I roll a 4, I roll a 5, or I roll a 6. So if I take the probability of each of those events, which we can look and see each of those probabilities are 1/6, just because it's a nice six-sided die. If we add all those up, we do get 1. The same would work if you were talking about flipping a coin or really just anything. If you add up all of the possible events and you add up those probabilities, you will get 1. If you don't, then you're either forgetting an event or you're not at doing the addition correctly. So there you go. All right. So we've been talking about what probability actually is a little bit. I want to mention 2 different types of probability. So we've been talking a lot about, like rolling a die or flipping a coin or something like that. And what I've sort of not done is I haven't said specifically how we're actually rolling that die or flipping this coin. And how we do this is there's 2 different ways. We could do it theoretically or we could do it empirically. And in a theoretical sense, this is more saying, hey, mathematically, like what's the probability that a coin lands on heads? I'm not actually going out there and flipping a coin. I'm just using my knowledge and using math to figure that out. If I contrast that with empirical probability is kind of like I'm running an experiment or I'm doing something. So maybe I flip a coin 5 times and I get heads twice and I get tails 3 times. Based on this experiment, the probability that I get heads is equal to 2 out of 5, which is 40%. And now we know that 40% is not actually the probability of getting heads, but based on this experiment, that's what this is saying. So empirical probability is not necessarily perfect, but a lot of times that's kind of how we have to figure these things out. Maybe it's not so cut and dry as just flipping a coin. Maybe I'm asking, what's the probability that that a random number you pick is prime? Well, that's going to be really hard to sort of figure out theoretically. The math on that would be tough. So maybe you just go and you ask people on the street. You say, "Hey, pick a random number," and and then they tell you a number, and you record whether it's prime or not. And then you just do that, maybe 10, 100, 1,000, 10,000, a million times, and you just count how many times people gave you a prime number or they didn't give you a prime number. And that's empirical probabilities. That's kind of just like going out and taking data down and using that data to tell you what the probability should be. Obviously, this scenario shows that it's not going to be perfect because in a theoretical and a perfect world, the probability of a coin landing on heads is 50% because it's either heads or tails. And so the question is, where do these theoretical probability and empirical probability sort of meet? Where do they match up? And where they match up is if you do an empirical study. So if you do an experiment, and here I'm doing it I'm flipping this coin 5 times. But if I keep flipping this over and over and over and over and over, and I just keep on going forever, and I flip this coin an infinite number of times, it's going to work out that I get exactly 50% heads and exactly 50% tails. Maybe I flip it 1,000 times. So I don't flip it an infinite number of times. But after 1,000 flips, it's going to be pretty close between heads and tails in getting 50-50. It might be a little bit off, but it'll be close to 50-50. And so empirical probability just has to do with like running an experiment and just sort of writing down the data and just using your data to get a probability. And theoretical is saying, well, mathematically, like what should happen. Empirical is what's actually happening in the experiment that you're running. And obviously, I could run an experiment and this could happen for me, heads, tails, tails, heads, tails. You could do the same thing. You could off to the side flip a coin 5 times and you might get something completely different than me. You might get 100% heads because maybe you just get lucky and you get 5 heads. And so we got to be careful about empirical probability. We're mostly going to talk about theoretical probability, maybe occasionally empirical, but mostly we'll deal with theoretical probability just because it is more exact. All right, we've kind of done this just a little bit, and I haven't really called out to it. I've just kind of done it, and maybe it was confusing, maybe it wasn't. But if we're actually want to calculate probability here, we have sort of a formula, if you will. It's kind of more. It's not so much as a formula, more as just a way to do it, sort of as a method. But we might say that the probability P of an event occurring, which I can just say P equals, I can also denote it by P of event. So I might say P equals probability of heads on a coin, maybe flipping a heads on a coin. It's the number of outcomes of that event. And actually, let's not use heads here. Let's say we're rolling a die. I'll say roll an even number. That'll be a little bit better. So the probability of this event, and in this specific example, probability that I roll an even number. What I'm going to do is I'm going to take the number of the number of outcomes of the event and divide that by the number of possible outcomes. What I like to do first here is ask myself, what's this denominator? What's the number of possible outcomes? And when I'm thinking about rolling a die, I'm saying, well, there's 6 choices. There's 6 things that I can get. I can get a 1, 2, 3, 4, 5, or 6. And so there's 6 possible outcomes. And then I just ask myself, how many of those are even? Right? And because that's what I'm looking for. I want to know the number of outcomes of this event of me rolling an even. Well, I can get a 2, a 4, or a 6 when I roll that die to get an even. So that's 3 possibilities. Let's kind of clean this up a little bit. So we've got 3 over 6 right here as 3 sort of choices for evens divided by 6 possible choices. And maybe instead of choices, I could use the word outcome. That'd be a little bit better. This would tell me that my probability is 0.5. Actually, let me write this out differently. We'd simplify first to 1/2. I could write that as 0.5. I could write that as 50%. And unless I specify, any of these are fine as your final answer. This 3/6 would not be okay because it's not simplified, but 1/2 would be okay, as is 0.5 or 50%. So let's go ahead and use this idea. I like to call this sort of method, this formula, just like sort of the counting method, because a lot of times we really just count things up, count the possible outcomes and things like that. So let's go ahead and use this sort of counting method to answer an example question here. So what's the probability that I roll a number greater than 2 on a die? Well, if I go ahead and say, hey, okay, the probability is number of outcomes that I roll greater than 2. And then I divide that by number of total possible outcomes. So I'm being very explicit here in sort of what I'm writing out. Just want to be careful with it. So on a die, the number of total possible outcomes is going to be 6, right? We've said that before. I can roll anything between a 1 through 6. So there are 6 total possible outcomes. And the number of those that I roll greater than a 2 is going to be if I roll a 3, a 4, a 5, or a 6. If I roll a 1 or a 2, those don't work. But these all work. And so I'm counting 4 outcomes here that make it so that I have rolled greater than a 2. And so we're just going to go ahead and put a 4 up here. I could simplify this to 2/3, and then I could write 0.6 repeating. I could also say 66.6 repeating percent right there. Any of these would be perfectly acceptable answers. I'd probably just leave it right at 2/3 and just call it a day. But there we go. So that's the probability that we roll greater than a 2 on a die. And we're just sort of using that counting method. So let's go ahead and do another example here. So what's the probability that I pick a spade from a deck of cards? And so here we want to be we want to be careful. We want to make sure that we actually understand our deck of cards. If you're not familiar with what a deck of cards look like, I highly recommend doing a quick Google search of just like a deck of cards. There's some nice images that just show all 52 total cards. And so you can take a look at that. We will be doing several examples with considering a deck of cards. So a deck of cards has 52 possible cards in there. And that actually right there, that just gives me, let me copy this right here. Give me a second, copying that. Let's actually paste this over here. So P is the number of outcomes that I pick a spade. And so we just said this, there are 52 cards in a deck of cards. So my denominator is going to be 52, because that's saying that the number of total possible outcomes is that there's 52 different cards that I could pick. And of those 52 cards, 13 of them are spades. So spades are one of the suits of a deck of cards, along with clubs, diamonds, and hearts. And so there's 13 of each of those, 13 times 4, giving me the 52 total cards. So there's 13 spades out of 52. If I simplify this, I get 1/4, which I could write as 0.25. You could also write 25%. And any of these would be an acceptable answer. As I've said before, I'd probably just leave it right at 1/4 and just be done. And so there you go. That's the probability that you pick a spade. Just kind of another example of using this sort of counting method to just count up the number of ways I can pick a spade and divide that by the number of total possible things that could happen. So let's go ahead and wrap things up by looking at this idea of complement probability. So a new thing here. And let's consider an event E that's occurring. So we'll do an example where we say that E is going to be that I roll greater than a 2 on a die. And then if we want to know what the probability of E not occurring is, we actually have a formula for that. Before we get into that formula, I'll mention that the probability of E not occurring, we denote that by E prime. So we put this little tick mark, this little apostrophe right after E. It's pronounced E prime or E complement, probably more so E complement. And the probability of E complement happening is 1 minus the probability of E happening. So basically it's saying, if I know the probability that something occurs, to find the probability that it doesn't occur, I can just do 1 minus the probability that it occurs. And there you go. Let me be very clear. This right here is not a multiplication. This is saying the probability of the event E. And so there's no multiplication going on right here. So let's go ahead and do an example here. What is the probability of not rolling a 2 on a die? Well, we saw before, and actually no, we didn't quite do this example before, but let's say that E is the probability that I roll a 2. or excuse me, E is the event that I roll a 2. E complement would be the probability that I don't roll a 2. It'd be that event. So what we could do is we could say, hey, P of E, well, the probability that I roll a 2, that's just one of the possible 6 outcomes. So P of E prime, using our complement formula, is going to be 1 minus P of E. And we see right there that P of E is 1 minus 1/6. So we end up with just 5/6. And that's our answer right there. And so this is a way that we can figure out certain probabilities of things not happening. Now you might just look at this and you might say, well, why couldn't I have just ignored all of this with rolling a 2? Just said, hey, I want to know what happened, what's the probability I don't roll a 2? Well, I can roll a 1, 3, 4, 5, or 6, which is 5 possible choices out of the 6. That's fine. You get the same answer. I'm just showing this sort of example here because there are certain scenarios where it's a lot easier to calculate the probability of something happening directly. So then you can just use this formula to find the probability that it doesn't happen. And we'll see examples of that, but for now, we'll just kind of use this very simple example. And also maybe you've already done a problem where you found the probability of rolling a 2 and you already figured all that out. So now you can just go straight to this formula and just plug in that answer you already found. So maybe, in certain problems, maybe that's a whole lot of work to find the probability of something happening. So now if you want to find the probability it doesn't happen, you just save yourself a lot of time. You can just do 1 minus the probability that it does happen. And that's complement probability right there. We'll go ahead and actually just leave that as this intro to probability lecture, and that'll be it.